Hello and welcome back, everybody. Today we will be talking about the Riemann sum of as a limit. So in the last section, we talked about how to estimate the area under the curve using rectangles that are height of the left-hand side, the right-hand side, the middle, or also maybe using like say trapezoids. Today we're going to talk about, well, what happens when we want to be as accurate as possible. So that means we want to use as many partitions as possible. So as a recap from last time, we said that, hey, this is very simple if we were to use maybe like say 1, 2, 3, or 4 partitions, but then it gets more complex because the thinner those partition becomes, the more work you actually have to do, the more math you have to do. So ideally, I would like to use maybe like say infinite number of partitions. And so that's where the idea of the limit comes in, because what happens if I have infinite number of partitions, limit as n approaches towards infinity, hint hint. So that's what we're going to be discussing for today. Okay, so now what I want to do is I want to talk about how to solve or set up a Riemann sum that becomes a limit problem, and then maybe be able to plug it into a calculator, or maybe plug it into a computer to have it solve for us, or maybe we know how to solve for the limit, and then be able to also work backwards to be able to look at a summation with a limit problem and to say, oh, this is the area under the curve and this is what I'm trying to solve for. So here's a quick recap as to what we did last time. So here's an example where I want to find the integral from 0 to 1 of x squared dx. So that means I want to find the area under the curve from 0 to 1. So you can see the picture that's on the right hand side. F of x is equal to x squared. Now I want to estimate the number, I want to estimate what is the area under the curve using n number of partitions. So first we're going to say that, oh, this is going to be the sum of every single one of those rectangles. So that's why you see the summation of base times height. Now, what I'm going to do is I'm going to go ahead and solve for each case when n is equal to 1, and n is equal to 2, and n is equal to 3, and so on and so on and so on. Basically, what the answer will be if I have n number of partitions. So in the case of the first one, which is n is equal to 1, if you have just one partition, is 1 times f of 0, which is equal to 1 times 0. And by the way, this is using the left-hand rule if you haven't noticed already. Then for n is equal to 2, if we have two partitions, the setup would be this right here, and then this would be the result. N is equal to 4, this is going to be the result right here, and we're going to just go and write it all out. And for n is equal to 3, this is what you're supposed to get, and n is equal to 5, this is what you're supposed to get. So this is all just kind of like from last time. But unlike last time, what I'm not going to do is solve for it numerically, but rather instead, I want to take a look at each one and see if we can generate a pattern, so then that way we can figure out what is happening when n is approaching towards infinity, right? So you'll notice that as n increases, you have a number of terms that's increased. But the more important part is that if you look at the inside, you can see that there is a pattern that's being generated. So for example, n is equal to 2, right? Then you have 0 and then 1/2. Then for n is equal to 3, then you have 0, you have 1/3, and then 2/3. And then the 4 is going to be 0, 1/4, 2/4, 3/4. And then for n is equal to 5 is 0, 1/5, 2/5, 3/5, and 4/5. So yeah, I'd like to think that there's a pattern. For the base part is the same thing. You'll notice that it's 1/2 for n is equal to 2. For n is equal to 3, it's equal to 1/3. And then for n is equal to 4, that's 1/4. And then for n is equal to 5, that's equal to 1/5. So by writing it like this, again, we're going to try to come up with a pattern for this. And here's the pattern that I'm noticing. The outside, the base, it's going to be 1 divided by n, where n is the number of partitions. Whereas the inside, now this is the part that's a little bit harder to swallow, but hopefully you can kind of see it. It's going to be a fraction of a setup for here, because you're taking that partition and you're breaking it into n number of parts. So it's going to be f of 0, then you have f of 1 over n, then you have f of 2 over n, plus f of 3 over n, plus 4 over n, and so on and so on and so on, like in all the cases above, all the way into the last partition, which is f of n minus 1 over n, because we're using, again, the left-hand side. Notice that for every single part, right, for n is equal to 2, the last one is going to be 1/2. For n is equal to 4, the last one is going to be 3/4. And then the next one over here is going to be 2/3 for n is equal to 3. And then for n is equal to 5, you have 4/5. So yeah, that matches with what I have then. And finally, we can go ahead and say replace f of whatever with the function x squared. So f of 0 over n, that becomes 0 over n squared, because f of x is x squared again. Then the next guy becomes 1 over n squared. The next one becomes 2 over n squared, and then 3 over n squared, and so on and so on and so on, all the way to the last part, which is n minus 1 over n quantity squared. Well, right there, that's going to be my answer. If I can somehow find what this sums up to be as n approaches towards infinity, then we actually have our area under the curve. So it's just a matter of being able to solve for that limit, and that's what this section is about. So finally, what I'm going to do is I'm going to go ahead and write this in a more compact form, which is the summation form, and that's where this guy over here comes in. So notice that the starting counter is at I is equal to 0, not I as an imaginary number, but as a variable. And we're going to go up all the way to n minus 1 because, again, it's the left-hand rule. And then the inside, well, the function is just I divided by n, where I is the counter and n is the number of partition. And the reason why it's squared, well, again, it's because f of x is equal to x squared. So you can see that this is really just f of xi, like I said in the previous part. So all of this right here, that is going to make the height. That's going to be the summation of all of the height then of the rectangle. Now this part right here, well, that's where the base comes in. And if you're wondering where the 1 comes from and the n come from, well, the 1 is because that's the size of the interval, right? From 0 to 1, remember, I'm trying to find the area under the curve from 0 to 1 of x squared dx. So that's where the 1 is coming from, whereas divided by n because there are n number of partitions. So if we can somehow find a way to solve for this summation, right, then that means that we have our answer. And is there a way we can do that? The answer is yes. We'll save that for the next time. But for right now, we just want to be able to recognize that this is going to be our final form for the time being. Okay, so this right here represents the area under the curve from 0 to 1 of x squared dx. Okay, all right. Let's look at another example similar to this. So then that way you can kind of get like a better feel of it or the grasp of it. So the next question is, well, what happens if I want to start at 0 and we want to go all the way to 4? So area from 1 to 4 for x squared dx. So here you can see my picture, right, on the right-hand side. You can see I'm not starting at 0 again, but instead I'm going to start from 1 to 4. Well, the idea is still the same thing. I'm going to go ahead and use base times height. According to our picture, well, I think it looks like it might be good if I break it into 3 partitions because that's nice and even. So let's start with that right there. Let's say for n is equal to 3, what happens there? Well, if n is equal to 3, then we have the base, which is 1. So that is going to be the outside right there. Notice it's 3 divided by 3 because 3 is the size of the base, and we're dividing it into 3 equal partitions. So that's why it's 3 divided by 3. And then the inside, the height, well, that's going to be f of 1, and then f of 2, and then f of 3, because we're referring to the left-hand side of each one of these. Can I use the right-hand side? The answer is yes, and you'll see how that actually works out if I use the right-hand side in just a little bit. Nonetheless, the area is then going to be the summation of these heights, and then multiplied by their same respective base, and then that will be our answer then. So that's for n is equal to 3. But again, I don't want to write it in a form where I just want the numerical values, but rather in a form that I can recognize a pattern so we can get something else out of it. So this time, let's say, okay, let's go ahead and break it into 6 intervals. Then, in the same manner, I'm going to sum up every single one of the heights from the left-hand side. And then notice on the outside, it's 3 divided by 6 because once again, it's the base, which is equal to 3, but divide by 6 because I have 6 partitions. Each one of those partitions has a base of 1/2. So that's where that came from. So in the inside, I'm going to go ahead and clean that up. And then afterwards, I'm going to go ahead and write it in another form that is going to help us see things a little bit better. You'll notice normally I'll stop at where the red is, but this time I'm going to go a little bit further. I'm going to go ahead and say that instead of 1.5, right, squared, I'm going to go ahead and say 1 plus 1/2 times 1. And then for the next one at 2, I'm going to say 1 plus 1/2 times 2. And then the next one, I have 2.5, which I'm going to write as 1 plus 1/2 times 3. What's happening over here is I'm showing you that I'm moving to the right by a certain fixed amount, which is 1/2. And then the counter next to it, the 1, the 2, and the 3, tells you how many of those partitions we need to move to the x value that we actually want. So this is basically setting it up so then that way I can write it in that sigma notation. So next, 1 plus 1 half times 4, and then 1 plus 1 half times 5, and so forth. Okay, so that's for n is equal to 6. Now if I write that up, this is what the summation equation actually looks like then. So 3 over 6, right? And then we have a total of 6 terms, but we're starting at I is equal to 0. So this is going to be the 0th term. This is the first term. This is going to be the second term. This is I is equal to 3. This is I is equal to 4. This is I is equal to 5. We're going to go up all the way to 5. And like we said, we're going to go ahead and write it as 1 plus the size of the base multiplied by what partition we're actually at. So then that way we can get the corresponding height. So hopefully from there you can kind of see like a better idea as to what's going to happen then. Well, if you're able to kind of catch on as to what's happening, right? And you know what? I think maybe what I'll do is I'll write this for n is equal to 3. That's going to say 3 divided by 3 multiplied by the summation of I is equal to 0 all the way to, you have in this case 3 terms. Here is I is equal to 0. Here is I is equal to 1, and then here I is equal to 2. So that means we're going to go up to 2. And for this one is going to be the same idea, right? It's going to be 1 plus 1 multiplied by I, and then raised to the square power. Again, 1 right here, because that's the size of the base, multiplied by the, I guess, the partition that you want to be at. Well, hopefully from here you can kind of see what's actually happening. Now we can hopefully conclude what happens if n is infinity, or there's infinite number of terms, or if there's n number of partitions. So now we can go ahead and now we can go ahead and write this all out. If we have n partitions, right, then my guess is that this is what's going to happen. You're going to have 3 divided by n, which again, the 3 is because that's the length of the base from 1 to 4, multiplied by the summation of I is equal to 0 all the way to the last one, which is going to be n minus 1, because remember, on the left-hand side is always 1 less than the actual number that you want to end up with. And then for the inside right here, it's going to be 1 plus 3 over n, which is the same thing, right, as what's on the outside right here, because this 1/2 is the same as this 3/6 over here, multiplied by I quantity squared. So this right here would then be my sigma representation of the area under the curve, and we're going to throw a limit as n approaches towards infinity in front, because again, we want infinite number of partitions. But there it is. That is basically what I need to throw into a computer or a calculator in order to solve for what's the area under the curve. Okay. Now, do we need to see how the hot dog is made every single time we do this problem? The answer is no. You should be able to hopefully connect from the very beginning, which says the area under the curve from 1 to 3 of the function x squared dx, straight into the form of this summation by looking at how things are actually working out. Note here that the idea is this guy is going to be my base, and this guy right here, that's going to be my height, and you're always going to start with the initial piece, which is the lower bound of 1 in this case, and then you're going to add 3 over n times the I, which is the represented partition. Nonetheless, I think it's probably better if I just kind of jump straight into an example so you can see what I mean by this. Okay. So what I want to do for each one of these is write it as a write each finite integral as a Riemann sum with limits. So basically take what I did and write it in a Riemann sum form, so then that way I can like maybe throw it into a computer or ask my TI calculator to solve for me. So here's how it works. First, we're going to look at the base part. This is saying the area from the area under the curve from 3 to 10. So to me, that's going to be 10 minus 3 divided by n, because that's the size of the base of each partition, and then multiply by the summation of every single one of the heights. Now, this is the only part that's going to be difficult. So it's going to be the function, right? And for each of the x, you're going to replace it by whatever height that you want to correspond to the partition. So my starting point is supposed to be at 3, and then we're going to say plus 7 divided by n, because again, 7 divided by n represents the size of the base, how much you're moving to the right each time. Multiply by a counter to tell me where is that height going to be, like which partition you want it to be. And that's going to be my x then. and then multiply by sine of the same thing, 3 plus 7 over n times I. The only thing now that we have left is to say where I is starting and where I is ending, which in this case is from 0 to n minus 1. And then we're going to put in front limit as n approaches towards infinity. And there we go. That is going to be our answer then. So this is what we're going to be plugging in into our calculator. Okay. Now, sometimes you might not actually see it like this. Sometimes you might see it like this. Limit as n approaches towards infinity of 7 over 10, which is, 10 minus 7, 10 minus 3. But the part that's, a little bit different is this over here. They might say I is equal to 1 all the way to n, basically having a shift in that summation, and then everything else is the same. So negative 3 plus 7 over n times I times the sine of 3 plus 7 over n times I. If this ever happens, it's still the same answer. All that means is that this right here is using the right-hand side instead of the left-hand side partitions. But if you have infinite number of partitions, I don't think it really matters if you're using the left-hand side or the right-hand side, because both are going to be pretty close to the actual answer that we want, so long as n is approaching towards infinity. Okay, let's try this for the next one over here. Do exactly the same thing. So first, we're going to go ahead and say limit as n approaches towards infinity. And then the first part is, let's look at the base. It's going from 6 to 16. So that's going to give me 10 divided by n. That's my base part. And then the summation of, let's go ahead and write the other one. I is equal to 1 all the way to n. Or if you want, you can say I is equal to 0 all the way to n minus 1. Doesn't matter which one. The inside is going to be the function. So ln of 7 plus sine of, and this is the part where, again, it gets tricky. All the places where you see an x, you're going to go ahead and replace with that setup that I just gave you. So my starting number, which in this case is 6, plus 10 over n, because that's the base and you want to chop it up into n number of partitions, times I. So that right there, that is going to be my x value that gets replaced when you put it into this equation. And then plus 1, and then close the parentheses, and there you go. So this right there would be the limit notation of the Riemann sum then. Okay. This time, hey, what if I want to go backwards? What if I want to represent, what if I want to know what is this Riemann sum actually asking for with the limit? Like, what is the area under the curve that I'm trying to solve for? So here, just working backward, now we have limit as n approaches towards infinity. Let's see, for cosine of pi plus 2 pi over 3n squared plus 1 times 2 pi over 3n. So if I were to kind of like work backwards and just kind of like recognize what part is what, well, I can still probably do the same thing, right? So let's see if I can write it. I think this is probably a little bit easier. First off, I noticed that there is a pi down here, so that tells me that that's most likely going to be my lower bound. So that's pi. Going all the way to where? Well, that's where this next part comes in. The 2 pi over 3 that you see consistently over here. So that tells me that's the size of the base. So it's going to be pi plus 2 pi over 3. So let me write that in. Pi plus 2 pi over 3. And my function, now this whole thing, that's supposed to be x then. So that's going to be the cosine of x squared plus 1. And then we're just going to go ahead and write the dx part. Okay. And by the way, if you're wondering by now, what is the dx notation? Why is it there? Well, it's because it's to represent, again, the partition, right? This integral sign is telling me that I want to find the area under the curve. So that's going to be the summation of every single base times height. This right here, that is going to be the height of the equation at any corresponding part. And this right here, that's going to be the base. Okay, so that's, where the idea of summation of base times height comes in. But nonetheless, there you go. That's going to be my integral then. Okay, let's look at this last one over here, just to make sure that everything's okay. So first, it's going to be the integral, right? The area under the curve from where to where? Well, here, looking at inside the parentheses, I notice that I'm starting at -5. So then that means that that's going to be my starting point. Then the next part, which is consistent with the base, is that this is 10n and this is 10n. And by the way, if those two are not the same, then that means this is a bogus problem and you wouldn't be able to solve for it. It has to be the same thing. So the 10n is telling me that the base is going to be 10. Well, -5 plus 5, right? Negative 5 plus, oh, sorry, 10. So that's going to be 5 then. So we're going to go ahead and end at 5, start at negative 5. My function is going to be the square root of 25 minus x squared and then dx. So once again, this matches here, and this right here matches right there. So there it is. That's going to be my answer. So it's saying find the area under the curve from negative 5 to 5 of square root of 25 minus x squared. Oops, sorry, my handwriting's really nasty. Dx. Hey, here's an extra cheat. Here's kind of like a treat for you. I think we actually know what this is numerically. This is going to be the following. The 25 minus x squared in the square root, that is supposed to be a semicircle, right, with a radius of 5 to negative 5. So according to this problem, what I want to do is I want to find the area under the curve of this circle. Well, I think that's easy enough. This is just a geometry problem. The area of a circle is supposed to be pi r squared, which in this case is 5. And since this is only half of the circle, then that means I need to multiply by 1/2. So then that means that this numerically is equal to 25 pi over 2. Okay, can you do that every single time? The answer is no, but it's nice if you can.